Welcome to this course on energy conversion and storage techniques. So today, as a conclusion of your first unit, we'll be seeing about energy units and conversion. So we have been seeing about different types of energy storage devices: mechanical, thermal, electrical, chemical. So each of these energy storage is expressed in a different unit. So in our last few course lectures, you would have seen that we have been talking about units such as joules, watt, and also BTU. So what are all these units? And when you integrate them, we need to have a unit conversion. So we are going to be seeing about why these units are important. Is there an international system for it? And the units which are applicable for each and every one of the systems which we have seen in the first unit. So why are units and conversion do they matter? First and foremost point is the quantification. So quantification of a particular energy is very important, which should be understood throughout the world. So let's say we give out a particular energy production in a particular plant and say it is 200 joule. That 200 joule should be understood by any person in any language. So quantification and its understanding universally is very important. Second one is we need to be able to compare technologies, compare production methods. We should be able to compare the techniques which we follow here to another technique which has been developed in some other part of the world. So without these standardized units, comparing is going to be very difficult. So for example, which is given, the thing which is given here, when you're going to compare the output of a solar panel to the energy content of coal. So solar energy is a renewable form of energy which is being currently being explored extensively, whereas coal is energy which has been used for many centuries as fossil fuel. So when you want to compare these two and say that solar energy is almost equivalent to coal or this particular panel is much better than the energy which is produced from a coal, you need to have a standardized unit. Without having a standardized unit, it's impossible to do a comparison. The third point is you set a foundation for any calculations. So whether it's going to be engineering design, efficiency analysis, economic evaluations of a particular energy sector, everything is going to be dependent on a particular unit and its accurate conversions. So when you're talking about engineering design, engineering design involves multiple units placed one after the other. So each of the unit will have a calculation, each of the unit will have a particular efficiency, and each of the units is going to have a economic evaluation. So when you're going to combine all these things in an overall plan design, you need to have a specific unit and probe and required conversions. The last point is for facilitating communication related to energy. So you need to have a clear and unambiguous communication among scientists, engineers, policymakers, and also the public needs to understand what each of the units refer to. So energy exists in various forms: mechanical, thermal, chemical, electrochemical, nuclear. So we have seen about all of these things in our last few lectures. So each form can be measured using a specific unit which is tailored based on its nature, and they are ultimately related. So we are going to be seeing what are the units which are used for a mechanical system, what are the units which are generally used for a nuclear system, what about a chemical system, and how these things can be related with each other. So understanding these units help in comprehending energy conversion processes where energy transforms from one form to another. So the choice of unit often depends on the scale of energy being considered. So we have the basic unit which is a joule. Whereas when you go for much bigger systems or when you're going to consider larger areas, you go for kilowatt, megawatt, and even terawatt. So depending on the scale of the system which you're taking into consideration, your unit also will vary. So we are going to be seeing about the International System of Units, which is called SI unit, which has been used globally. So the unit is Joule. So Joule is the foundation of energy measurement in the SI system. So Joule is actually 1 Newton meter. It represents the amount of work done by a force of 1 Newton acting over a distance of 1 meter. So when you convert it into the base units, you have kg meter square per second square, because Newton basically is force. Force is nothing but mass into acceleration. So mass kg, acceleration meter per second square. So when you talk about joule, it's going to be Newton meter. So it is going to be kg meter square per second square. Now, when you're going to introduce the concept of again time into this, you have watt, which is nothing but 1 joule per second, the amount of energy used per second. So 1 joule per second is called watt. So this is the basics of your energy. You have a joule, and joule per second is watt. Beyond this SI system, so while SI system is a standard, other unit systems do persist, particularly in specific industries and regions. So some other units which are also commonly used are BTU, British Thermal Unit, and pound foot of energy and horsepower. So each different sectors and different industries have their own specific units. But although they have a specific unit, still we have energy conversion numbers. So you can easily convert, let's say 1 BTU is equal to how many joules. We have a conversion scale. So familiarity with these units is crucial for interpreting historical data and engaging with specific sectors. Accurate conversion between the systems and SI is essential for global collaboration and data analysis. So this is a very important point. We need to understand the system which are followed in our own sectors. So a very important thing which has to be noted is the perils of unit confusion and the importance of accuracy. So using the wrong unit or incorrect conversion factors can lead to significant errors in calculation and analysis. So also it's called as dimensional inconsistencies. So let's say you say the machine is operating at a speed of 5 meter per second, whereas someone else around the globe understands that 5 feet per second. Your entire calculation based on this assumption is going to be thoroughly flawed. Yeah. So in engineering, such errors can have severe consequences for design, safety, and efficiency of energy systems. In terms of policy and economics, an inaccurate energy data can lead to flawed decision making. Last point, always double check the units and conversion factors, and always use a reliable source for conversion values. So a joule to second is very important, and how do you take into consideration? So sorry, a joule to calorie. So if you take the conversion, a calorie is equal to 4.184 joule. So certain sources may even round up the value and say 1 calorie is equal to 4.18 joule. So there you have an error of that 0.004. So it's very important to use a reliable source of your data. Another example is 1 BTU, British Thermal Unit, is equal to 1055 joule. If you round it up to 1000 joule, you're going to have a lot of error related to that. Okay, so first and foremost, joule. So mechanical energy, most of the systems we are going to be using this. So work done the kinetic energy, potential energy are all expressed in joules. When you're talking about heat energy, that is thermal energy, again, most of the industries use the system of joule. When you're dealing with electromagnetic energy, that is the energy which is stored in a field, or the photon energy, they are also expressed in terms of joules. Chemical energy, so energy is stored in the form of chemical energy, so it is expressed in terms of per mole or per kg. So much of joules energy can be stored in a kg of this particular chemical or per mole. So next one is watt-hour. So where do we use this particular system, and what are the different values which are commonly used? So watt-hour is nothing but 3600 joules, which is the amount of energy consumed or produced at a rate of 1 watt for 1 hour. So 1 hour has got 60 minutes, and each hour has got each minute has got 60 seconds. So an hour has got 3600 seconds. So that's why we have 1 watt hour is equal to 3600 joules. So when you see about our household energy consumption, we always express it in terms of 150 units, 200 units, or 250 units. So 1 unit is nothing but 1 kilowatt hour. So it is a common unit for building residential and commercial electricity consumption. So 1 kilowatt hour is equal to 1000 watt hour. That's equal to 3.6 into 10 power 6 joules. So when you're coming into a household usage, we talk in terms of kilowatt hour or 1 unit. When you're going to move into a much larger zone, or maybe a society or a district or a state, then you use larger terms such as megawatt hour, gigawatt hour, terawatt hour. Okay, so large scale energy generation, storage, grid level analysis and all, we use the bigger terms of gigawatt hour or even terawatt hour. So this is mainly used for energy consumed or energy produced. The next one is BTU, which is British Thermal Unit. This unit has been used for many years. So it is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at a specified temperature. So here you see the use of temperature in another scale. Generally we use Celsius, whereas here we use Fahrenheit, and even the weight of water is mentioned in terms of pound. So it is a system which is commonly used in the United States for measuring the energy content of fuels such as natural gas, propane, and all types of heating oils like furnace oil and those sorts of things. So what is the conversion? 1 BTU is equal to 1055 joules. So understanding BTU is important when dealing with older equipment or US centric energy data. So let's say we are developing a system for a US client, or you are developing a plan for a client who's there in US or it's going to be established in the USA. Their terminologies are going to be totally in terms of BTU. Whereas we follow SI, so we'll be mentioning everything in terms of joules. So it's important to ensure there is a concurrence while doing the design. Next one is calorie, also kilocalorie. So historically, it is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So here you can see here all the units are SI units. 1 gram of water by 1 degree Celsius. Okay. So 1000 calories is also called as a 1 kilocalorie, and it is commonly used to express the energy content of foods. So this terminology, this is 50 calories. It's all related with energy stuff, energy food products. So the conversion is 1 calorie is equal to 4.184 joules. Also 1 kilocalorie is 4184 joules. So it is less common in general energy discussions, but it does play a very important um, terminology when you're discussing about biomass energy, which is used in fuels. The next one is electron volt. So whenever you're going to be talking about solid state physics or atomic physics in specific, we are going to be talking about the energy there in an electron or the amount of energy transferred. So all these things are expressed in terms of electron volt. So it is the amount of energy gained by the charge of a single electron moving across an electric potential of 1 volt. So only when you have a potential difference, your electrons flow. So when your potential difference is 1 volt, the amount of energy gained by the charge of one electron moving is called 1 electron volt. So the conversion is 1 electron volt is equal to 1.602 into 10 power minus 19 joule. So it is the basic unit which is used in all your electrical calculations and physical calculation, especially nuclear and solar cell materials. Okay, so still now we have seen many units: joule, calorie, BTU, and now electron volt. Next, we are going to be seeing about another unit which is very commonly used in your CGS system, which is called ERG. So it is centimeter gram second system. It is another system similar to your SI unit. So 1 erg is equal to 10 power minus 7 joule. It is less commonly used in your modern scientific and engineering works. The other one is pound foot. So it is the amount of work or energy in the imperial system. So here this also you may encounter this terminology in your older mechanical engineering literature. Olden equipments will be expressed, the energy produced or stored will be expressed in these terms. So 1 feet LB is equivalent to 1.356 joules. So the next one is therm. So this is specifically used in the natural gas industry in United States. So these are all now we are going into the larger level. So you can see the quantity one therm is equal to 100,000 BTU. Now we already know 1 BTU is equal to 1055 joules. So when you convert to joule, one therm is equal to 1.055 into 10 power 8 joules. So understanding a therm is essential for interpreting your natural gas bills and statistics. Of course, this is commonly used in United States, but still a basic understanding is very important of all these units when we go into the we're going to be dealing with chemical engineering sector. Now the other unit is barrel of oil equivalent or ton of coal equivalent. So these are units which are used in a global scale. So a measure which is used to normalize the energy content of different fossil fuels related to that of one barrel of crude oil. So you would have very commonly seen this unit usage of this unit. This country has got so many million barrels equivalent, barrel of oil equivalent, or we have 18,000 ton of coal equivalent. So these are all used to talk about the energy content of different fossil fuels present in their particular region or country. So what is ton of coal equivalent? It normalizes the energy content of various types of coal to a standard ton of coal. Okay. So these units are crucial for aggregating and comparing national and global fossil fuel reserves and consumption. So if you take a energy report of a particular country, this energy analysis of let's say India or any other country, you will find all the units expressed in terms of this. A very common thing which is expressed now is the amount of fossil fuel present, the number of years in which we will be able to have this and the amount of energy which you are currently using. All these things will be expressed in terms of barrel of oil. Okay, so till now, what all have you seen? So we have explored the various types of fundamental energy units, and we have seen about the basic fundamental unit, which is joule, and we have seen about units like watt hour and BTU, which are prevalent in specific application region, and we have seen about the conversion, the relationship between these units, which is very crucial for any study related to energy. Now, again, we are going back into our system. So we have watt, which represents the rate at which energy is transferred, used, or converted. So power signifies how quickly energy is being utilized or produced. So these are some of the examples in which it is represented. A light bulb may consume 60 watt of power, while a solar panel might produce 300 watt of power under certain conditions. The next one is about kilowatt, megawatt, gigawatt, and terawatt. So kilowatt generally used in your household and small commercial power consumption and generation. For example, your rooftop solar systems are all in terms of kilowatt. When you go for bigger, larger power plants or large industrial facilities, the energy which is produced or used, it is in terms of megawatts. Now, when you're talking about your gigawatt, you're going to be talking about larger regions or countries. And when talking about terawatt, you're going to be talking on a global scale. Okay. Another important unit is your horsepower. So horsepower is very commonly seen. We get this term when you're talking about the power generated in your supercars, 200 horsepower, 600 horsepower. So where does this come from? So it is a unit of power which is in the Imperial and US customary systems. It is used to compare the power of steam engines to that of draft horses. Yeah, so it is started all with steam engines. So one mechanical horsepower is equal to 745.7 watt. In the electrical system, one electrical horsepower is equivalent to 746 watt. It is still used to rate the power of motors, engines, and other mechanical devices. So very commonly we see this in supercars. The energy is explained in terms of so many horsepower. Now the last one is your volt ampere or volt ampere reactive, which is used in your AC power, alternating power. So the unit of apparent power in an AC electrical circuit is calculated as a product of RMS voltage and RMS current. Okay. Now what is VAR? Voltage ampere resistive reactive. It is the unit of reactive power in an AC circuit, representing the power that oscillates between the source and the load without doing useful work. Okay. So these units are important for understanding the capacity and efficiency of electrical equipment like transformers and inverters. So now we have talked about the basic unit systems, and now we are going into something called as energy flux. So all units are talked with reference to certain mass or certain time or certain volume. So everything is respect to something. Okay. So energy flux. So in terms of solar radiation, it is measured in watts per square meter. So it is the represents the rate at which energy is incident on a surface area. So very commonly used for solar radiation. So how much of energy is obtained from the sun per square meter. So in one particular square meter, how much energy is obtained in terms of solar radiation. So that is called energy flux. So it is crucial for characterizing the intensity of solar radiation, thermal radiation, and other forms of energy transfer. Total energy received over time is then calculated by integrating this flux over the area and time. So when you talk about energy flux, watt per meter square, now if that is integrated over the entire available area of the earth exposed to the sun, then you can get the total amount of energy received. So these are used in calculations related to solar energy, especially the efficiency and the available energy and how much energy is being obtained from a particular solar panel, what is the efficiency of the panel. All those calculations are depending on this energy flux. The next one is power density. So it is important for characterizing the performance of energy storage devices like batteries and supercapacitors, indicating how much power they can deliver relative to their size or weight. So size becomes a big important parameter as well. For example, when you are going to have an electric vehicle, you're going to have a minimum amount of space where the battery can occupy, or the vehicle will have certain restriction related to the size of the battery, the weight of the battery, the volume of the battery. So there you're going to have an important term which you need to define, which is called as power density, also called as the power output per unit volume or mass. So this unit is specifically used in terms of for batteries only. So next one is kilovolt ampere. It is used for rating electrical equipment. So it is used to rate transformers, generators, okay, and also other AC electrical equipment. Kilovolt hour reflects the total power that the equipment must be able to handle, including both real power and reactive power. Okay, so this is about your kilowatt ampere system. Now coming to your renewable energy systems. So you have a lot of new systems coming into the picture like wind power, hydropower, solar power. So for example, first you talk about wind power, the total turbine output is rated in terms of watt, kilowatt, megawatt, depending on the capacity of the turbine. So performance is characterized in terms of power coefficient, which is a dimensionless ratio. Hydropower is determined by the flow rate of water, that is the cubic meter per second, and the hydraulic head, resulting in power units like watt and kilowatt. The last one is about solar power. So solar power is mainly based on your photovoltaic systems. So these are rated by their peak power output in watt or kilowatt under standard test conditions. The next one is about specific energy. So as discussed in the last few lectures, we are seeing about the amount of energy per unit kg or volume or mass. So specific energy is the amount of energy that can be stored per unit mass of a system. It's typically measured in watt hour per kg or megajoule per kg. So, so as already discussed before, the same point, a key metric for energy storage devices is especially applicable for EVs, portable electronics, because portable electronics, the key thing is about it being portable. So weight plays a major role. So higher specific energy means a lighter device can store more energy. Next is about energy density. So the amount of energy per volume. So watt hour per liter or megajoule per liter. Next one is called heating value. So this completely is related to the amount of energy which is available in a particular fuel or a chemical or a solid fuel. So the amount of heat released during the complete combustion of a specified quantity of a fuel. So this all started in steam engines. So amount of energy is can be gotten from coal when you use it in a steam engine. So automatically we can find out, okay, how much time a steam engine can run. So it all started with that. It's also called as calorific value. So it is expressed in terms of kilojoule per kg or megajoule per kg in terms of solid or liquid fuels such as coal, biomass, oil. We are talking about chemical reaction, everything is based on your stoichiometric value. So molarity. So how much kilojoules of energy can be produced per mole, or how much energy is there in your natural gas in terms of BTU, British thermal unit per cubic feet. So cubic feet is also a terminology used for your volume. Next one is your energy intensity and energy elasticity. So energy intensity is nothing but a measure of the energy efficiency of a nation's economy. It is calculated as the ratio of energy consumption to the gross domestic product or GDP. So a lower intensity means it indicates greater efficiency. Energy elasticity. So it is the ratio of the percentage change in energy consumption to the percentage change in the economic output. So it indicates the responsiveness of energy demand to the energy growth. So these terminologies are all related to the policy makers. So with this, we will stop this class. So in the upcoming next lecture, we'll be seeing about specifically about the solar radiation and different types of energy which we get from renewable sources such as geothermal, ocean energy, biomass energy. So we'll be talking about the units and conversion in those systems in the upcoming lecture. Thank you.